In a few minutes, Professor Stephen Serjeant, Professor of Astronomy, will speak on the subject Citizen Science and the Data Avalanche. When I was reading the blurb about it, I was fascinated, Stephen, by your two questions. Did you know that people are better at classifying tasks than computers? Interesting. And can outsourcing help us to classify data of the universe? Just before I get on to that, I just want to draw your attention to a number of upcoming events here at the Open University in the School of Physical Sciences and in the wider STEM faculty. This is one in a series of talks which are celebrating the Open University's 50th birthday. It's a series of open STEM talks. There are details of the upcoming talks on the Open University STEM faculties' various accounts. And that's where you need to be to book places or upcoming talks. However, I'm also going to just quickly alert you to one or two other talks that are being organised by the School of Physical Sciences, and the place where all of the things are together is on the Open University School of Physical Sciences website. And if you just Google that lot, you'll find yourself in the right place and look at events. So just quickly to highlight the upcoming events, and there's a few things that have firmed up since last week. So on Thursday the 10th of October, again at 6, we've got another Stephen, Professor Stephen Lewis, who will be talking about a blue planet to a frozen desert, exploring the environments of Venus, Earth and Mars. Then on Wednesday the 23rd of October, now confirmed for 5:30, we have Professor Jocelyn Bell-Burnell, who, as some of you know, discovered pulsars back in 1967 when she was a PhD student at Cambridge, and she has been a staff member here at the Open University. Those of us who have been around for a while have worked with Jocelyn. And she's going to talk about an unexpected adventure. Both of those are now open for booking, and particularly Jocelyn's talk, I would advise if you want to come that you get tickets fairly quickly, because I think it will sell quite quickly. Sell, you know what I mean? It doesn't cost anything. Then after that, we've got two talks coming up that aren't yet on the website. We've got, in November, we've got me and Clem Herman and Cara Morris. We're three women who've had unconventional careers in STEM, and we'll be having a conversation around some of the issues that flags. Later in November, we've actually got a lunchtime talk, which is Professor Russell Stannard, who was a very early staff member here at the OU, who'll give a more historical approach. We've got 3 of the Institute of Physics talks here in the Beryl Lecture Theatre on Tuesday evenings. The details are on the flyer that's out at the front, but we've got Carol Haswell speaking, Ulrich Kolb and Simone. Is it Sternilio? It's not a name, I know, but there's 3. And then last but by no means least, we've got another couple of our professors in the School of Physical Sciences, Dave Rothery and Carol Haswell, in the inaugural lecture series on Tuesday the 14th of November, again here. So a few housekeeping items. The first is that we're not expecting a fire drill, so if the alarms go off, get out of here. The doors are there and over behind you, up there at the back, and if you could assemble on the car park outside. Just to remind everybody that this talk is being streamed online. So when we get to the questions at the end, if you could just wait for Katrina and Alice to come around with a microphone, because otherwise the online audience won't hear your question. And we will be giving time, we will be collecting questions from the online audience as well. Afterwards, we invite you to join us downstairs in the Beryl Cafe for drinks and nibbles. Yes, help in drinking the wine, very gratefully received. I think that's the housekeeping. So I'd now like to talk about Stephen. Stephen joined the Open University from the University of Kent in 2006, and he was previously at Imperial College. He's had a very, very wide-ranging research career, which has taken a slight change of direction recently, and that's, in a sense, what you're going to be talking about, I think. So Stephen is an astronomer, he's a professor of astronomy, and his interests in astronomy are in starburst galaxies, infrared astronomy, and strong gravitational lensing. It's recently taken him in the direction of big data and citizen science, which may be terms you know, they may not, but I'm sure that Stephen will explain that. And so on the subject of citizen science and the data avalanche, I'd like to ask Professor Stephen Serjeant to take over. So thanks, Stephen.
Thank you. Thank you very much, everyone. So we are enormously lucky to be alive right now, because we are at a genuinely transformative moment in science, because the amount of data that's coming in is so big and so complex. It's just understanding the data is itself a huge challenge, and scientists need help to do this. So there's never been a better time to participate in the process of scientific discovery. Meanwhile, the capabilities of machine learning, artificial intelligence, have increased amazingly quickly. And so the question is, can machines rake through all of this data for us? Can AI take over this process of scientific discovery? Or at least some of the processes of science? Will we need scientists in the future? Okay, what does it mean to be a scientist? What will it mean to be a scientist? So what I'm going to do in this talk is describe the huge growth in participating in science through citizen science, through crowdsourcing experiments, and also what machine learning, what AI can do and what it can't do for us. So although I won't directly answer the question of what it means to be a scientist, I hope you'll have enough information to come to your own views. I should also explain the blizzard of logos we got here. A lot of this work has been funded through big research grants. Most of the stuff I'm going to show is through the Asterix project. That was European Horizon 2020 infrastructure. We've got 2 new projects just starting up, Escape and Reinforce. They're building the European Open Science Cloud for open access to data and building citizen science experiments. So, plugs over. I want to ask the question, what does a scientist look like? And well, there was a study done here on this question. There was some, I think, 12-year-old children or 10-year-old children who were asked to draw a picture of a scientist. And you know what it's going to look like, right? It's going to be weird, geeky blokes, basically, old blokes as well. And they then, the students then, were sent on a field trip to, maybe it was CERN, maybe it was National Physical Laboratory or something, and they got to meet real members of the scientific community, and then drew their pictures afterwards. And these are I think the same children's pictures, so the same children and their revised pictures. And this is what they did. And in fact, I don't know if you can see this, the guy is saying, "Sup, y'all." That's lovely. So what I'm going to be doing in this talk is hopefully challenging your ideas of what a scientist is. So I'm going to structure this talk in 3 parts. I'm going to describe the leading, what I think is the leading citizen science platform globally. It's called the Zooniverse. I'm going to describe how the Zooniverse came into existence. And then I'm going to talk about the data avalanche that we have in astronomy, but not just in astronomy, in all kinds of areas of science. And machine learning, how machine learning, artificial intelligence, is helping us interrogate this data stream. And then I'll talk about the synergy between humans and machines, because it's not really a case of machines taking over from the scientific process. It's about humans and machines having a virtuous circle. Okay. So let's kick off with how the universe happened. So there was a paper back in 2007 does the universe have a handedness? And I think there's like a law that when a paper poses a question, the answer is always no. So the thesis of this paper was that there was an underlying chirality to the universe, a handedness. So what this chap had done is he'd taken images of spiral galaxies and he classified them automatically with his some algorithm as left-handed spirals or right-handed, clockwise, anti-clockwise. And he mapped them on the sky and decided there was some statistical evidence for a global spin of the universe. And I read that and, this is being recorded. I'm not allowed to swear, I suppose. Oh. Please don't. Oh, I've got the social media people going, please don't. Right here. Okay, so I saw this paper and I thought, that's a load of... Right, okay, so you know what I'm thinking here. So, can't be true, just can't be true. So this data set was 84,000 galaxies or something like that, 87,000 galaxies, and I had an item on my whiteboard, all the things I was wanting to do, and I was like, eyeball all 87,000 of these things, just to check, and it was days and days and days and days and days of work, and I've got a proper day job, so I'm not going to do that. So, but it was there, this aspiration, but. There was another group who saw the same paper and they came up with a different approach. Their idea was to ask volunteers to classify things as left-handed or right-handed. And take a much bigger data set, and the data set from nearly 1 million galaxies. And with such a big data set, they reckoned it would take an expert 3 to 5 years, even working 24 hours a day, 7 days a week. So you're not going to do that. I mean, that's going to sit on nobody's whiteboard and get done, right? So they decided to crowdsource it, to ask for volunteers. And this was an idea from, I think, Chris Lintott in Oxford and Kevin Sherwinski and a few other people. Karen Masters, I think, may have been involved then. Anyway, a group of really, really good people. And oh my goodness, they discovered this rich seam. It was an amazing thing. They expected 20, 30,000 volunteers worldwide. They got 100,000 volunteers, making 40 million classifications. They just chomped through this data set. And they discovered that there is a great public willingness to participate in the process of scientific discovery. And this was, I think, a great discovery. So we've got a video that we made about this as part of the Asterix project. So let's see if the sound works and we can make this happen. And if the sound doesn't work, I promise I won't swear. And you'll see if you can listen out and hear who the narrator is.
60-second adventures in collaborative science. Number 1, citizen science. Since the study of science began, it's been expanding and evolving faster than you can swipe left. Today, scientists are using technology that would have blown the minds of their predecessors. But the problem is that things like our swanky new telescopes mapping space are producing so much information that even our swanky modern computers can't handle it. Then, in 2007, Chris Lintott and the team at Galaxy Zoo had the idea of asking volunteers if they could help sift through images from space. And it worked. People from all over the world helped out and not only classified and even discovered new galaxies, but spotted and named other astronomical objects as well. This project soon became a collection of projects, the Zooniverse, ranging from decoding ancient manuscripts to spotting penguins in Antarctica. All you need is an internet connection and everyone in the world can become a collaborative scientist. Now that is mind-blowing. If you enjoyed this clip,
you don't need the plug. Did anyone recognise the name? The person who gave the talk? Yeah, David Mitchell, who's many, many things on television. Anyway, if there's one message I would like you to take away from this talk, it is the following. Okay, citizen science is not outreach. Okay, People think of citizen sciences as, public engagement, like giving talks to brownies or something, right? It's not. As a scientist, you think about citizen science as a tool for doing science. It's like a multi-headed biological computer, okay, for doing complex classification tasks. Okay, it's a tool like a spectrometer, and I don't want to be any pejorative sense of tool, because I know there are lots of very dedicated, wonderful people who are contributing their time and their effort and their mental processing power to these tasks. But as a scientist, you've got this wonderful facility of people that you want to deploy on something that really matters. Okay, so citizen science, it can help with outreach, but it's not for outreach. Okay. So this Galaxy Zoo experiment, it was a tremendous success. There've been, I've got a slide here from Galaxy Zoo. There's a Galaxy Zoo 2, Galaxy Zoo Hubble, Galaxy Zoo 4+, lots and lots of galaxy classifications. And you can see the numbers of classifications there, just vast. And if you look at the amounts that individuals have contributed, this is a representation of that. Each square is an individual, and the area of the square is the amount that those people have classified. And you can see that about a third is lots and lots and lots and lots of small contributions. But there's a lot of it that is a few very dedicated people who have poured time into this, and they've become very expert in the classification tasks. And another very nice result is the unexpected things that have come out of this. So this is from Galaxy Zoo publications by the type of discovery. So 41 of the papers were quotes expected. So you realised that there was an amount of data coming in, you knew the nature of the information that was coming, that the nature of the classifications. You figured that you would be able to make a study about, let's say, galaxy morphology as a function of colour and environment or something. So you knew that science was going to come and you'd be able to write a paper on it. So that 41 of the papers were expected, but 9 of the papers were serendipitous discoveries, so things that were not planned at the outset of the experiment. Okay. Oh, and by the way, I should say the universe does not have a handedness as far as they can tell. Although there is a very nice result about humans not having a symmetric perception. So the likelihood of a thing being classified as clockwise or anti-clockwise, if you just give a random image, it's not 50-50, right? So in fact, if you take an anti-clockwise image and you flip it, you don't get the same mirror image classification. So human perception is not completely chiral. It's not achiral, rather. So that was a surprise. Anyway, so in terms of other serendipitous discoveries, there were the green pea galaxies. So these are galaxies that the volunteers classified as green peas. So they're small unresolved galaxies, dwarf galaxies, that have a lot of star formation, and that star formation results in strong oxygen emission lines, and those emission lines are in the green filter, so it means that these little galaxies look like green peas. So there's a whole population of galaxies there. There's also this weird splodge. So they were asked to classify galaxy morphologies, and one of the volunteers spotted a splodge, a weird splodge underneath one of the galaxies. Now, the Galaxy Zoo process has sort of a talk board, a forum, an online forum where people can discuss what they've seen. And the woman who found this, she was from the Netherlands, and so she called it in Dutch a thingy in Dutch. And if anyone here can speak Dutch, I do apologise for my accent. But I know it as voorwerpie, which is thingy in Dutch. Okay, so she called it a thingy, a voorwerpie. And this thingy, this voorwerpie, was followed up by the Hubble Space Telescope and by many other facilities. And it turns out that what it is it's a light echo from a dead quasar. So you have an accreting supermassive black hole in the galaxy at the top. And it's drawing in all the gas and dust, and that's being whipped around and compressed and stuff and heated up, and you've got a quasar, and it's blasting out lots of ionizing radiation, lots of light. And that ionizing radiation is hitting cloud of gas. Okay, and that cloud of gas gets lit up and ionized and gives off these oxygen emission lines and so on that I was talking about before. And but then the quasar stops accreting and it becomes dormant, and you've just got a black hole sitting, I'd say quietly, but sort of on its own in the center of the galaxy. And so the gas on the outside is no longer being irradiated by this blast of ionizing radiation. So what it's doing then is it's radiating away what energy it still has. So it's in that moment. You're catching the system in that moment where the quasar has died, but still the surrounding stuff is just radiating away the last of the energy that it's received. So it's a very rare thing, and it's one thing that citizen science is very good for. It's picking up rare events. And this was completely unanticipated, and this has been a subject of a lot of studies from professional astronomers. And the discoverer, Hanny van Arkel, has actually co-authored some of those papers. And this is her with, you might recognize some of the other the people in that picture, and she, Brian May is a very keen astronomer and has a PhD in zodiacal dust. So I mean, he's absolutely a kosher astronomer. So so then the question is, you have all of these people pouring their time in. Why are they doing it? Well, there has been a careful analysis of this, and it seems that there are a few questions that make a successful citizen science experiment. How easy is the experiment? How easy is the task? How beautiful is it? How important is the question? There's got to be a sense of you're doing something worthwhile. How much am I learning? It's really important to have educational materials built in, and for the scientists to engage genuinely in discussions with the volunteers. And the last one is my favourite. How famous could I get? So, there are some questions, some citizen science experiments where that's a serious thing. So, like SETI at home, right? You could be the person who gets a wonderful wow signal from another civilization, or you could be the person who discovers a planet around some other system, or you could be the person who discovers a rare pulsar or something like this. But so there are often opportunities in citizen science for a person to make a tremendous discovery. So I'm just going to highlight some of the citizen science experiments that we've been doing. There's a lovely experiment by Andrew Norton on superWASP variable stars, is asking for volunteers to classify light curves from stars. You're looking for pulsating stars, you're looking for binary stars, and because of these things that are happening in real time, you get changes in the brightness, and you want to look at these changes in the brightness and somehow characterize what's going on in these systems. There's another project, so actually it's a lovely project, it's called Penguin Watch. So the idea here is it's an ecological experiment. There are cameras in Antarctica, and you want to quantify the penguin population. And this is important for the krill in the sea, which is important for fisheries, which is economically important. It's important for understanding the ecology. It's important for understanding the effects of climate change. There's all sorts of reasons, but it's also really cute because you get penguins and you have to click on the penguins and count their eggs and so on. There's an old weather logs experiment where you're transcribing very old weather records, and again, that's important for climate change. And it's very hard to get a machine to do this. As you know, like with penguins, it's very hard to tell a computer, where are the penguins? How many penguins are there in this picture? A human is actually much better at that than than a machine, because one penguin can stand in front of another penguin. It's one of those. They're quite annoying. They don't line themselves up. There's another. I don't know if this quite counts as citizen science, but it's certainly using the technology, and that's through disaster relief, using remote Earth observation to look at where the sites of natural disasters have happened. So you look at the satellite pictures from before a natural disaster and afterwards, and you say, well, this is an area here that has been particularly badly affected, and the relief crews have to dive in to that particular area because that's where the need is. So this is, there's a very real human importance to this problem. And if you look at where the natural disasters tend to occur, and you compare that to where the volunteers are, actually there's an almost perfect anti-correlation. So this is one example of where the developed world is helping the DACList countries, helping the developing world. That's one good thing, putting science to good use. Okay, so next I want to focus on the data avalanche and machine learning. And the biggest data avalanche in astronomy, I think, is coming from the Square Kilometre Array. It's going to come from the Square Kilometre Array. This is a huge next-generation radio telescope that's being built on two sites. It's being built in South Africa and in Australia. And the data volumes are vast. I mean, there's a case for saying that it's not a telescope, it's a computer. It's a big computational project. So this was a headline from 2011. The SKA telescope to generate more data than the entire internet. Okay, so there's more data than the entire 2011 internet. And it's just, the data rates are just vast. Just astonishing. So you want to you want to be ready to mine this big data set. So there are already citizen science experiments up to try and mine data sets like this. So there is a lovely experiment, Pulsar Hunters, looking for pulsars in radio data. You're trawling through images like this. And pulsars are these neutron stars that, it's the discovery by Jocelyn Bell Burnell, yes, of neutron stars with squirting out radio emission along two axes, and that axis is offset from the spin axis, so you get this lighthouse flash that goes past you. And the Square Kilometre Array will be marvellous for finding these things. In fact, it was once originally called the Hydrogen Pulsar Telescope. So neutral hydrogen and pulsars were the key science goals. And it's not just in astronomy. There's also the Large Hadron Collider at CERN. In fact, it's getting an upgrade called the High Luminosity LHC. And I've got a graphic here of the increases of data volumes from the current LHC out to the High Luminosity LHC in 2026. Oh yes, I've got a mouse, and comparable to the Square Kilometre Array. And this is Google's entire Internet Archive of 2018. So, I mean, these are vast data sets. And with the Large Hadron Collider, there's already citizen science experiments going. There's the Higgs Hunters experiment. You're looking through particle collisions, trying to characterize what's going on. So you get data like this, and you're being asked how many branches are there, how many particles coming in, particles coming out. And we have a new project just starting up called Reinforce, and that will be creating another CERN-related citizen science experiment. So people can come in and do particle physics and really participate in scientific discovery. There's also the Large Synoptic Survey Telescope, which is scanning the sky, looking for things that change. They're looking for supernova explosions, for example. So a whole area, big data area, is opening up in astronomy in the time domain. So you tend to think of astronomical images as static, and actually the universe is a very dynamic place with gamma ray bursts and gravitational wave events and supernova explosions and colliding neutron stars and so on. And the optical flashes are what you'd be picking up here. And this is a good time to introduce a particular sort of machine learning technology. So there is a machine learning technology called neural net. And the idea here is well, it's using the biological metaphor of a neuron, or perceptron, you could call it. So you have, basically, you're thinking of a neuron as a thing that takes some inputs, some numbers, and turning it into some outputs. And there are a few free parameters, and you can tune in changing the inputs to outputs. Okay, so 0-point offsets and scalings and so on like that. Okay, but it's a very simple operator. Okay. So, and that's not going to do very much for you, but what you can do is stack them up and nest them. So you could have a bunch of inputs coming in to a bunch of neurons that then do their simple operations and spit out their outputs to another set of neurons, and then again to another set of neurons, and so on, and then spit out to outputs. And it turns out that this methodology can approximate any algorithm, okay? In fact, you don't need to nest them like this. You can have one great long strip of neurons, and that very inefficiently, but it can approximate any algorithm turning inputs into outputs. And that's partly why this technology has really taken off, because you can, if you've got a complex classification problem, you don't know what the algorithm should look like, you can use this to make a machine do it. The trouble is that every neuron has a set of free parameters. Okay, so you've got a lot of free parameters to train. And even though we knew that we could do this, or I say the royal we, it was known that we could do this since maybe the late 1960s or 1970s, and it goes a long, long way back, this thinking. It's only recently become possible to train tens of thousands or hundreds of thousands of parameters. Okay, so this technology has only really been applicable recently. So there is a variation on this for the time domain, and I'm going to show you. So here we are with our neuron. Takes an input, okay, does something to the input and squirts out an output. And then the output gets fed back into the neuron and modifies it. So this becomes a self-modifying thing. Okay, so then we've got a modified neuron. Takes some inputs, squirts out some outputs, and that gets fed back in again, and again it modifies it. Okay, so this is the sort of technology you want to have if you're waiting for a particular response. Okay, so you want the machine to change state when something happens and you're waiting for it to change state. So that's the technology that is used with Siri. So if you say "Hey Siri" to it, it will respond because it has been trained to respond to that, or Cortana, or Alexa, or all these other things. They are trained to listen, wait, and respond to a particular thing. Okay, and so in astronomy, the way this works is like this. You have so this is some time domain data. Where is it from? Maybe it's the Zwicky Transient factory. I'm not sure, but you have data in two wavelengths, a green image and a red image, and you're observing a galaxy, and then you have a flash that goes off. It changes, the flux goes up. So that's the top plot. And the bottom plot is the classification that it is making in real time. And you see that it starts from just pre-explosion, nothing much happening, and then this green curve ramps up. So supernova type 1a. And so actually it slightly surprises me because it seems to start ramping up before much has happened. So quite what it's doing there, I don't know. So and if you can get an early alert, then that could be very, very important if you don't have too many false positives. So this is where machine learning is trawling the data set and giving us some useful information. And then when you've identified a flash from a supernova explosion or something, and you can go and look at that part of the sky in lots of different wavelengths, and you can see, is it a gravitational wave event? Is it giving off light and gamma rays or X-rays and so on? You can find out a lot about the physics. So we are now become we're now in an age of multi-messenger astronomy. So you wait for a flash at one wavelength and you follow your flash up in lots of other wavelengths. So we have a multi-wavelength, multi-messenger astrophysics at the moment. It's really the way the field has gone. So I've got a video on this. Let's see if this one works.
"60-second adventures in collaborative science."
Dodgy
Number
moment.
3, multi-messenger science. Imagine a world where every new discovery was a closely guarded secret. A frustrating world where human progress would be severely limited. This could be particularly damaging for modern science, where one group not being aware of an important discovery by another could hold back scientific understanding in general. Which is where Asterix comes in, a European Commission project to connect research teams so they can share data and information quickly and easily, far more than a punctuation mark. A great example of this collaboration is in investigating fast radio bursts. This isn't the static you get when you're adjusting your radio, but a random flash of radio noise which only lasts for nanoseconds. So it's only with scientists across the world working together that we have any real chance of working out what these radio bursts are and where they come from. In addition, by building a community of scientists and citizen scientists, one discovery can lead to many more, which is good news for the human race.
Jolly good. So I'm now going to talk a little bit more about other sorts of machine learning. I'm going to talk about a particular technology called generative adversarial networks. And the idea here is you're trying to create simulated images. Okay? So you have a machine for making simulated data, and you have another machine which is designed to try to tell the difference between the real and the simulated. And you're training both of these things up simultaneously. Okay. So let's say your task is to make pictures of a cat. Okay, so you've got real pictures of a cat and you've got simulated data. So you run that past your discriminator and no, definitely one of them is fake. So you iterate a bit and get a slightly better picture of a cat, maybe, and still the discriminator is no. But after a while, your machine's starting to get better and the discriminator has to work a bit harder. Okay. So, I mean, that's the methodology in a nutshell. So, 5 years ago, 2014, there was an effort to use this technology to make simulated images of faces. Okay, and this is the sort of faces that were created. And yeah, they look fairly realistic. They're pretty blurry, but it's believable, right? Right, I'm going to stun you if you've not seen this before. This person does not exist. This is a simulated image of a person. It's just staggering. I find myself staring at this in awe. It's actually from a website, thispersondoesnotexist.com. It's an amazing thing. And when you've stared at these for a few times, you begin to understand what the machine is doing and what the machine is not doing. So it tends to be very good at reproducing textures. So it'll get the texture of a beard quite realistically, it'll get the texture of hair quite realistically, but it doesn't really have any sense of the three-dimensionality of objects. So, and as a result, it can get the background quite skewish. The backgrounds look often quite unrealistic, even if the people look more or less realistic. Often it can't, because it doesn't understand three-dimensionality, it muddles up the texture of hair coverings with hair. So you've got weird images like this where the hair is blurring into a scarf. And it also doesn't understand that people don't tend to wear asymmetrical earrings or have asymmetrical eye colour and all of these things. And sometimes it just goes mad. So we've got a hat here that turns into hair, and oh my God, what is coming out of her head on the right-hand side? You see on the far side. It's very strange. And sometimes the images are just, I mean, this to me is not a realistic image, but it's very striking. It's an amazing image. This one spooks me out. This one is actually from whichfacesreal.com. This is the first one that I got wrong. I didn't realise this was a fake image. I don't know if you see on near the OU logo, there's a little bit of fuzz that gives it away that it's a fake image, but I didn't spot that. So this is the first time that, if there's an equivalent to a Turing test, this one passed my Turing test. So, crikey. I've got a quiz for you now. There has been an effort to create, to apply this sort of technology, but to fine art and to the things that we really think of as intrinsically human. So there was an effort to create a new Rembrandt picture. I mean, that's probably, fine art, that's one of the hardest things you could do, I would guess. So one of these is fake. So we could do it as a show of hands. Okay. How many people think the woman is the fake image? Okay. How many people think the man is the fake image? Most people thought the woman. That was very interesting. But the man is the fake image. It's just, and the sensitivity of the man. My God, it's amazing. And now, to be fair, I picked not one of, in my inexpert opinion, not one of Rembrandt's best pieces to compare it against. So I made a slightly unfair comparison. But it gives you a sense of the level of the sophistication that's going into this now. And there are lots of other things you can play with online. There's a website called InspiroBot, which takes it has a natural language engine underneath it, and it understands a little bit about grammar and has a database of nouns and verbs and stuff, and it creates inspirational quotes. And it has a database of stock images that it puts underneath them. So, and sometimes it makes it spookily randomly makes a sensible point. Yeah, if you're laughing at irony, you really don't know what irony means. That's quite good. And I like this one. But natural language processing has gotten to the point where you can create fake news articles that look realistic. So there is a whole ethical talk that could be given about machine learning in this context. In fact, there was a research group that, one of the nice things about machine learning is people tend to make their source code public. So you can download it, you can play with it, you can optimize it. It's an open source community. It's rather wonderful, in fact. But in this case, the research team kept their code under wraps because they didn't want people to abuse this technology. And just to show we're bang up to date here, I want to show you an abstract that was circulated just a few days ago. And the abstract on the preprint bulletin board archive the title is On Extractive and Abstractive Neural Document Summarization with Transformer Language Models. We present a method to produce abstractive summaries of long documents that exceed several thousand words via neural blah 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 blah. I want to point out the punchline at the end. Yeah, the abstract above was not written by the authors. It was generated by one of the models presented in this paper. It's like, wow, what a plot twist! That was brilliant. So machine learning is really, really coming along. So where does that leave us? The synergy between human and machines is the next thing I want to talk about. So let's reassure ourselves. Things AI can't do. Okay. And one thing that AI can't do, that's weird, okay? So if you, you've got a machine trained to recognize faces. It will tell you where the faces are, but only the human is going to say, wait, there's a clown. There's a clown. Who put a clown in there? Oh my God, there's a clown. So humans, I guess because they have a much, much bigger background knowledge that they're bringing to bear on the problem, they're able to take a step back and say, wait a minute, there's something else going on here. And in fact, a good example of that is this Hanny's foreverb that I mentioned earlier on. This was someone taking a step back and saying, wait a minute, we're being asked to classify spiral elliptical galaxies and handedness and stuff, but there is this weird thing here. What's going on here? And you need a human to do that. An AI cannot do that. You need someone to be able to take a step back. And another good example of that is it's called the Zorilla problem in Zooniverse. So there is a lovely citizen science experiment called Snapshot Serengeti. And the idea there is you have cameras in the Serengeti and they want to record the ecology. They want to know what wildlife is there. And so, a lion goes past, or I was going to say lions and tigers and bears. Well, maybe you're not going to get the tigers in the Serengeti. But you could train a machine to recognize the elephants or recognize giraffes or something, or the things that exist in larger numbers. But there are some creatures that are so rare that you can't create a training set to train a machine to find them. And this is an example of one. It's called a Zorilla. I had no idea what a Zorilla was until I got into this stuff. But you need a human to be able to look at the data set and say, this is something else. This is not a lion or a tiger or a bear. This is a weird thing. Okay, another thing that AI can't do, and that's data collection. And there was a very nice experiment that we partly helped form and create, called a Cosmic Ray Extremely Distributed Observatory. And the idea here is to use the cameras on your phones as a high-energy particle physics detector. When you have all the cameras across the whole of the world, you can see if there is a cosmic ray event that is showering the whole of the Earth simultaneously. Okay, so you can, collectively, we can be a particle physics detector. And there's a video on this. I'm not going to show the whole video, but I think it's kind of fun. I do think it's a very beautiful video. You're using a camera to make dark frames. Glorious stuff, glorious stuff. The idea here is you have supermassive particles in the early universe that decay to very high energy photons, and they can collide with perhaps particles in the interplanetary medium, and that creates a shower that blasts over the whole of the Earth. I have a final David Mitchell animation on this here as well.
60-second adventures in collaborative science. Number 2, messengers from space. Mobile phones are very useful if you want to chat to friends or annoy people in a theatre. But did you know they're also intergalactic particle detectors? There's a very good chance that wherever you are, you're in a shower of subatomic particles from space. They're not dangerous, but they could answer some important questions, such as what dark matter actually is. Many of these particles originate in the sun, but there's a chance that decaying dark matter could also create cascades of particles. We'd need a detector the size of the Earth to measure these massive cascades, which might have some downsides. But something that has already spread over the planet is the mobile phone. So scientists developed apps to turn camera phones into mini particle detectors. And the Credo project has gone further, linking up citizen scientists to spot these rare cascades of particles. And if enough people join in, then their mobile phones do become a global detector. Just remember to turn it off in the theatre.
Jolly good. So, how do we combine the capabilities of humans and machine learning? Well, of course, at this point, I've got to show the obligatory Borg picture because it must be a physical law. You can't talk about this without doing that. Now, I want to talk briefly about a particular citizen science experiment to find strong gravitational lenses. So this is where you have a foreground galaxy almost perfectly lined up in front of a background galaxy. So you're seeing the background galaxy through the warped space of the foreground galaxy. And there's been a lot of effort from citizen scientists to trawl through big data sets to find these warps. So I don't know if you see the little curvy shapes there. That's the background galaxies that are being seen through the warp of probably a galaxy group there. Okay, so you're looking for these chance alignments where you have a background star, let's say, and a foreground deflector, and you get two lines of sight, or you get several lines of sight that can take you around to see the background thing, because you're looking through a curved space. So let's simulate this. I've got a very advanced simulation to show you. Let's firstly create a background star. Here's the background star. So let's put a transparent gravitational lens in front of this background star. It's a good look, hey? And let's crank up the mass of this background galaxy. And actually, this is I've used real gravitational lensing simulation software on this. This is it's accurate in that you can see that it conserves surface brightness, so the image stretches, it doesn't get fainter, and you get multiple imaging. You see he's got two mouths now. He's got a smiley mouth and a frowny mouth where his nose would otherwise be. So you do get multiple imaging. So this is genuinely realistic, but slightly more astrophysically realistic is images like this, where you have blue background galaxies here and red foreground galaxies and multiple images and so on. And these are the sort of things that are discovered by volunteers. So you can also accelerate the classification. This is where we start having a synergy between humans and machines. Okay, so what you could do, you could have the top path where the volunteers classifying the images, and then you can look and see whether there are any that are quite consistently being classified as either yes or no, and you can maybe weed those out. But then you get ultimately to a bunch of ostensibly well-classified subjects, and then you can feed that into machine learning. So you've got a set where people are convinced that these are, let's say, gravitational lenses, and then you can feed that into a machine learning, and then train the machine learning, and get that machine to collect up all of the easy, obvious things. And then you can refocus the volunteers on the tricky cases, and that makes the whole process much more efficient. So the machines learn from the humans. And there's been an experiment. This has been tested There's this has been tested using the Galaxy Zoo project, and it turns out that using the machines in this way is a factor of 8 faster than just chugging through and letting the volunteers classify everything. So it really is, it really makes a big difference. And we have a postdoc here working called Hugh Dickinson, who specialises in this technique of the virtuous circle between machines and humans. So, and he's already doing great work. We also had a project called the Muon Hunter. That was one of our Asterix-funded projects. The idea is looking for cosmic ray showers from muons, and you're looking for circles, pretty colourful circles in these high-energy astroparticle physics detectors. That's because you have it creates a shower which is conical, and they splat onto the detectors at a circle. So it's a very nice experiment. But what I want to show you is this: that I took this snapshot 5 days into our project, and we had 1.3 million classifications in the first 5 days. Just boom! And I'm amazed, actually. I mean, I think it's a lovely project, but I still don't understand what the magic sauce is, the special sauces that made it so amazing. In any case, now there is a Muon Hunter 2 project, and the idea is to see if we can train machines to do this by giving volunteers groups of that have been classified as the same. So here's a group of rings and here's a group of not rings. And you're asking the volunteers, has the machine got this right? And you're trying to create a virtuous circle between machines and humans here. But gravitational lensing is really going to explode metaphorically. With the launch of the Euclid Space Telescope in a few years. Now, Euclid it's a 1 meter class telescope. It's only a little bit smaller than the Hubble Space Telescope. It'll be mapping about half the sky, so you're getting nearly Hubble Space Telescope quality images over nearly half the sky. So this will be really good for finding those rare things like a foreground galaxy and a background galaxy warped around it. So if you could find them, that would be amazing. So we reckon there are about 100,000 gravitational lenses, strong gravitational lenses in the Euclid mission. But this will be among about 1 billion other galaxies. So this is a real needle in a haystack problem. So there has been an effort within the Euclid Consortium to create a lot of simulated images and try to train machine learning algorithms to find these among these gems among the chaff. And we've got 2 excellent grad students who've been working on this, Josh and Andrew Davies, Josh Wild and Andrew Davies. And we've got some lovely machine learning technology for this, but there was one research team that tried to do it the hard way. So there were 100,000 images simulated, and Neil Jackson and his team, Amit and others, they checked every single one by hand. They checked every single one and flagged the lenses and flagged the not lenses. So, and there was a time limit to this particular challenge as well. So they just poured all their time into doing this. But they did not win the challenge. The machines did better. So this leads us to the question, why are machines doing better than the experts? And so we set up a citizen science experiment, called it Challenge the Machines, to try to use the citizen volunteers who've previously been amazingly successful at finding strong gravitational lenses in other citizen science experiments, and try them on this data set to see whether they can do better. Because it could be just, the experts got tired or something. And for this particular classification task, I think the citizens are really good. I'm not sure that I would be as good as the best citizens. So there are some people who, you saw those plots of those squares. There are some people who really poured their time into this. So there are people who are very expert in this area. What I heard this morning was that, the volunteers chomped through this data in less than a week. It's all classified, and yeah, the early result is actually the machines are still doing better, but we need to, yeah, I know, wow, wow. So, and we need to unpick why that's happening, and that's what we're hoping this will do. So as part of this experiment, the Zooniverse created a Tinder-like mobile app. You can swipe left and swipe right for whether a thing is a gravitational lens or not. I've got an early demo version of it here. This is Hugh Dickinson demonstrating it. I don't know if you can see. You've got a gravitational lens image there, and you can swipe either left or right. You can swipe one way or swipe the other way. Ooh, yes. This was just a demo version. The full version is working now. So it's marvelous, marvelous things. So I just want to finish up now. I want to do a couple of quick adverts. There is a new citizen science experiment that Hugh was involved in starting up called Galaxy Zoo Clump Scout, and you're looking for clumps of star formation in galaxies. And we really do need human volunteers to do this, because it's of fundamental importance to evolution of galaxies, evolution of the morphologies of galaxies. And it will also be perhaps our first citizen science experiment that's at least facilitated through the ESCAPE Consortium. And also I want to point you to, I should say it's launching maybe in a week or two, so look out for that. I would like to also point you to the Planetary Response Network. So you may have heard in the news that there was a Hurricane Dorian, okay? They are looking for volunteers to trawl through satellite data right now, okay? So you can make a difference today to relief, disaster relief, okay? So please do. So I endorse this experiment, and please try it out. So just to finish off now, I've got a question. We started off with this question: what does a scientist look like? And I hope I have convinced you that the answer is this. Okay, so the end. Thank you.
Thanks very much. Is it human? That's the other question. Okay. I've got a couple of questions. Any in the audience or any online? Yes, there's one over there.
Hey, Stephen, thanks for the talk. I enjoyed that. Just a clarification, actually, really, on this. You talked about the gravitational lenses image, the 100,000 image, and the race to finish them. And you said the machine learning models did better. I just wonder what better meant.
Oh, okay, right. So there's a particular metric we use called the area under the receiver operating characteristic curve, which is you plot let me see if I can get this right, the numbers of false negatives and false positives, and you're looking for the better than random. Better than random would be a diagonal line, and you're hoping to get close to an area under this of 0, of 1 rather. Okay. So I mean, there's a balance between the amount of false positives and false negatives, and true positives and true negatives. So you need to make a choice of whether you care more about a complete sample or a pure sample. So in astronomy we call this reliability and completeness, and other fields call them type 1 and type 2 errors and so on. So anyway, under the metric that we chose, the machines did better in this balance between reliability and completeness. Yeah.
We do have one from online, which asks, are humans more accurate and yet less accurate than AI due to having emotions?
Due to having emotions? Well, people can get tired. So machines don't get tired. I don't know if you ever played a chess computer, and if you're playing a human, you can rattle a human, right? But you can't rattle a chess computer. So in a sense, emotions can they can hinder you, but they can also motivate you. Being competitive can help as well. So Yes. So I think the answer is yes. Humans are in a sense. Well, we have our advantages, and machines have their advantages. So I hope that answers the question.
Yeah, it's a really interesting one. But one of the points I was going to make is that we need to talk. I research, as you know, I research automatic marking of responses, answers to questions. And actually there's a huge echo in what you said. Human markers are very fallible. I mean, even the expert markers make mistakes. I've been the person... Yeah, the students watching. We do check it and double check it, and of course it's there in the thing. But computers, and there's an awful lot. But there's also stuff that computers can't do, and it comes in those very unexpected things. It's that how weird moment, isn't it, that you said? And I liked the idea of the emotion. That was really, really interesting. Andrew.
Yes, Stephen, you had a slide at one point. You know what AI can't do, and you had the clown and so on. Do you think that should have been what AI can't do yet?
We have a lot more computational capacity than any machine at the moment. So I mean, it's always dangerous to make these speculations, but I would guess that we're not in our lifetimes are we going to see anything close to that. And also humans, we interact with the real world, and we have a much bigger range of experience. So I'm confident, quietly, that we needn't be concerned about the yet. At the moment, but you make a good point that the field is moving on very quickly. In fact, it's startlingly fast, this particular machine learning.
Anything else? I've got a fairly... It's a really simple question. I feel a bit of an idiot asking it. It's right back to the beginning when you talked about what makes good citizen science. And the first part was how easy is it? Now, I'm guessing the sort of the right answer, the answer that I suppose what I'm asking is easy good or is difficult good? Because again, you can see that easy makes it easier.
Yeah.
But again, in attracting people to it, is there anything known about that?
Yeah. So I guess it depends how many people you want to engage. Okay, so if you've got a very simple swipe left, swipe right, you can imagine someone on a bus just doing some citizen science, right? But if you've got something really complicated, like you're trying to fold a protein or something, and you're trying to say, will it go this way? Will it go that way? Could I bind a molecule on there? Actually, that's horrendously complicated and computationally complicated as well. So you're not going to get hundreds of thousands of people doing that for you.
Yeah, okay. So people are quite happy with the quite easy, swipe right, swipe left.
Yeah, but there is a group of people who are content to work on very complicated, very involved tasks, but they're a much smaller fraction. So you tailor the science you want to do to the audience that will be receptive to it. Yeah.
Oh, that's great. Thank you very much. Can you just all join me in thanking Stephen once again? With apologies to the online audience who don't get the refreshments downstairs, the rest of you, if you'd like to make your way downstairs to say there's refreshments, then a chance to ask Stephen any more questions you'd like to have. As well as thanking Stephen, I'd just like to thank all of you for being here, and I'd particularly like to thank Katrina and Alice for running around with the mics, and again to the AV team. So thanks very much.
Thank you.
Thank you.